After divide and conquer, we moved on to what we call dynamic programming, and I went on for quite a while about why dynamic programming is kind of a misleading term, and we should just call it DP. Right? So DP is this concept that looks like this. So we can use dynamic programming, or DP, if our problem has one optimal substructure, and this means that the problem that we're looking at, that like the optimal solution to the problem we're looking at, can be easily derived from the optimal solutions to some number of subproblems. Okay, and so you can almost think about DP as working like this. DP says, if only I knew, I'm looking at the overall problem and I say, if only I knew this, right? If what I plug into this, into that blank right there, is the solutions to a bunch of subproblems, a bunch of smaller versions of the bigger problem, then we call this a DP algorithm. Then you can use DP to solve it. All right, so basically, this is one of the things we're looking for. The other thing we're looking for is overlapping subproblems, and so this is one of the things that makes DP different from divide and conquer. So if you think about an array, in merge sort we do something that feels a little bit like DP. Like the overall sorted array is composed of a bunch of smaller sorted arrays, but we don't call it DP because there's not overlapping subproblems. Each of those underlying arrays can be solved without knowledge of any kind of the solutions to the other arrays. Okay, they don't have any relationship to each other at all. So you can just solve the thing purely recursively and not think about memoization or that kind of thing. In DP, we have to be careful because we're usually looking at problems with overlapping subproblems. And the example I think that illustrates this kind of most simply is the Fibonacci sequence. So if I try to compute the nth Fibonacci number by starting at n and saying, well, first I've got to find n minus 1 and n minus 2, or f of n minus 1, f of n minus 2. If I set that up just purely recursively, I showed on the board how you end up having to recompute many of the Fibonacci numbers essentially an exponentially large number of times. And so you have a whole lot of extra work that gets done that doesn't need to be done. So DP tries to solve exactly the correct number of subproblems, like the fewest that we need in order to be able to solve the overall thing, and to do so in kind of a clever way. And so the example I like is the robot coin collection. Robot coin collection. And so the way this problem works is I have a grid, and I have some, let's say this is a 4x4 grid. And then I have some of these spaces filled with coins. Make it a 4x5 grid. And the goal, and I'll just say this without writing it out, but the goal is to plan a path for a robot that can only move down and to the right. Like there's no choice to move backwards or up. So plan a path for the robot that picks up as many coins as it possibly can. And so the book talks about how to use this, how to use a DP kind of approach to solve this problem. And then in the homework we asked, how do you do this if there's blockages? Like how would you modify this? All right, so here's the DP idea. So anytime you're trying to write a DP algorithm, think about what's the DP idea. So let's let f of I and j be a function that says, here's the most coins I can collect by the time I get to cell I and j. And in some places it's 0, in some places it's going to be more than 0. But this is it. It's the largest number of coins I can collect by the time I get to cell I and j. All right, so now I can write f of I and j recursively. Here's how it goes. F of ij is equal to, first, the number of coins in cell ij plus the larger of the largest number of coins I could get if I came down into this cell, and the number of coins I can get if I come from the left into this cell. Okay, so plus the max of f of I minus 1 and j, and f of I and j minus 1. Okay, and you could modify this if you're also allowed to come in diagonally, right? You could modify it easily that way. So this is the most that I could get from above, and this is the most that I could get from below, from the left. And it's certainly the case that I can only come from one of those two directions, right? I can't come from the right or from below because of my rules of the game. And so that means this has to capture the answer that I'm looking for. Okay, so if you want to think about this, we could write our input like this. And I'm not going to write pseudocode for this, but I do want to give you the idea of the algorithm and just kind of walk through this. So what if C is an array telling me where all the coins are? So containing the coins. So my C for the previous problem looks like this. So I've got 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1. Okay, so that's where the coins are, and if we reference it to the what I wrote up above, it matches. So there's my C, and so now I'm going to write my F array. And so I called F of I and J a function, but it's a function with a discrete pair of inputs, and so I can draw it as an array. Right? Even though you're used to thinking of functions as like having some mathematical closed form, you can also think of a function as just a table. Right, that maps coordinates to outputs, to numbers. So here's my F table. And so the problem in the DP algorithm is starting up here and just filling out the rest of the table. So what number goes in this box? Well, we take this box and plug it in, and then say now it's the larger of the number above and the larger or it's whatever in that same cell in C, plus the larger of what's above in F versus what's to the left in F. And so this ends up being 0. And in fact, the entire first row is 0. And if I want to look down the left, the entire left column is mostly 1s. So I get a 1 there because of that coin, and then I get a 1 here, here, and here because there's a 1 above it. Okay, so if I fill out the rest of this thing, I have to put a 1 here, and a 2 here, and a 3 here, and a 3 here, and a 1 here, a 2 here, a 2 here, 3, 3, and all I'm doing is every time I come to a cell, I'm saying, all right, right here, I'm comparing this number with this number and copying the larger one in, right? So the larger one goes in here. Now let me look down on the other side. So right here, I'm comparing 3 and 2, and the larger one goes in, except that I have a coin in that cell, I think. Yep, I've got a coin in that cell. So the larger one goes in plus the coin, right? So plus this coin. So I end up with a 4 in this cell. And then I end up with a 5 in this cell. And so what this table now tells me is that by the time I get to the bottom right, there is a path through this grid that lets me pick up 5 coins. And so let's just verify that that's correct. So our path, it says, does this. And so let's just follow this path. So I get 1, 2, 3, 4, 5. Sure enough, those are the coins that I get. So now what we did in the homework is I said, all right, let's augment this problem now with blockages and say, all right, now we get an additional array, a B array, where some flag in the B array says here's a blockage. Okay, so now with blockages. So a new array, B of I and J, is, let's say it's 1 if cell I is J, IJ is blocked. 0 if clear. And you can represent these blockages however you want. And so now what do I need to represent in my DP table? Well, now I need to represent that a cell is inaccessible. And notice it's not good enough to have my F mean only that how many coins I can get for getting there. Because there's 2 reasons that I might not be able to pick any coins in a particular cell. Either that cell's blocked, or the cell is inaccessible. I mean, sorry, or the cell just has no coins, and there's no coins available to pick it up. Right, so I need to be able to differentiate between these two things. So I can't just let 0 mean I can't get any coins here. I have to have another symbol that means this cell is inaccessible. Okay, this is really important. The algorithm is wrong if it doesn't have those two things, if it doesn't have some kind of way of distinguishing between no coins and inaccessible. All right, so f of I and j will be -1 if the cell is inaccessible. And notice I'm not using the word blocked, I'm using the word inaccessible. So if I and j is inaccessible, and 0 greater than or equal to 0 if I and j is accessible. Okay, so our new DP idea is when we come to a cell, first we have to check if it's accessible, and then if it is accessible, we can run the old DP idea. Right? We just can inherit the other algorithm. So our logic is going to look something like this. So if there's a blockage in a cell, ij equals 1, or right, so that cell could be blocked, or it could be that we're blocked from above and from the left, right? Those are the other ways. So or f of I minus 1 and j equals -1, and f of I and j minus 1 is -1. Okay, so the first part of our OR statement says this cell actually has a blockage in it. The second part of our if statement says even if this cell doesn't have a blockage in it, I can't get to it because I can't get to above or to the left. So if this is the case, then what do we have? Well, we have that f of ij equals -1. Whoops. No equals there. Equals -1. Okay? So that's case 1. Case 2 is that it's accessible. So this basically says now that cell is inaccessible. So the other case is we just use the old DP algorithm. Right? We just say f of ij equals c of ij plus the larger of whatever's up to the left and to the left and to the above. So max of f I minus 1 j, oops, that's a square bracket, and f of I j minus 1. All right. So now let's actually run this thing. So let's say here's our grid. So C is going to be the same coins. 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1. So there's our C. And now our B, our blockages, are going to look like this. So our B, and I'm just going to draw the blockages right on here in pink. Okay, so the blockages are going to be there, 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 and there. All right, so now what is our F table going to look like? I'll draw that below. So our F table is going to have a 0 in the upper left, 0 in the upper left, 0 here, and then this cell is inaccessible, right? And now look at the far right cell. That cell also is inaccessible, not because it's blocked, but because the cell to its left was inaccessible. Okay, there's no way to get to it. So now I've got a 1 here, but I have an inaccessible right there. And now look at this cell. This cell is inaccessible above and inaccessible to the left. So I have to make this cell inaccessible as well. So this cell is also -1. And notice that is despite the fact that there's a coin there. So you have to be really careful with this algorithm and make sure that you check inaccessibility in a distinct step from checking how many coins there are. Okay, so this cell is inaccessible because and there's no number in it, no number except -1, because the above and to the left is both inaccessible. And so then that holds for this one as well. So this one is also inaccessible because above and to the left is inaccessible. Let me fill out the left row. So I have a 1 here, and then that's inaccessible, that's inaccessible. And so now I can start filling out the rest of the table. So this has to be a 1. This is going to be a 2. This will be a 2. Then this number here will be a 2 as well. I have a blockage there. And then this is a 2, this is a 2, and this is a 3 and a 4. Okay. And so let's just backtrack the path. Like the path says we came this way. So slightly different path than before, which of course it has to be because we got fewer coins, and the blockages forced us to do that. And now if you look over here, of course that path is in fact the only path that gets us to the, well, I guess it's not the only path that gets us to the end, but it is the only way to pick up 4 coins. Okay. So there you go. So DP is all about thinking about how do you decompose the problem, how do you decompose a solution to the problem into kind of manageable chunks, and this is how we go about that.